Good afternoon, class. This is Mr. Bean here, and we're going to take a look at video number 2 here, looking at circular motion of a steel sphere here as it rolls down a ramp and goes around the loop here. So let's take a look at it and kind of watch, see what's going on here. We're going to go ahead and put it here, and we'll kind of watch it here and see what happens. All right. So it comes down here, so as the ball rolls down, it has normal force along the ramp here, and when it's on the loop here, we have to consider two things. What's the normal force here at this location, and also what's the normal force here at this location? Okay, those are two critical situations we have to look at. Now, what happens if we don't have enough speed here? What happens to the ball? Let's kind of watch what happens. Okay, so if there's not enough speed here, the ball will probably fall right here. That's because the normal force is approaching 0 at this location here. When normal force is 0, that means that the ball does not have enough force or speed to continue around the circular motion, and it will fall under the influence of gravity. So we need to investigate these two situations. Okay, and we're going to continue on with video number 2 here, and let me grab here. Let's go ahead and make our circle here real quick. Okay, so here we have a loop, but we only want to look at 2 locations for AP Physics 1. We want to look at here, and we also want to examine the situation here. So let's take a look here. Let's go ahead and draw a cart here, and a cart here like so. And here it is upside down, and we'll draw it here and here, and it'll be right side up. So we'll assume it's going in this direction here, like so. Okay, so here we want to look at the situation here. What's happening here in terms of normal force, gravity, and acceleration? Okay, so a couple of things. One, we know that from here, we know that the normal force is acting in this direction, and we also know that mg is also acting in this direction, and we also know that centripetal acceleration is also acting toward the center. It's center directed. So all 3 are acting in the downward direction. Therefore, we'll call going down being positive. So what happens is that we have here some of the forces on top. We'll call this the top region. This is the top. Equals mass times centripetal acceleration, like so. So on the top here, some of the forces, we have the normal force, plus we have mg is equal to mac here. So the normal force, just like the elevator problem, we have here m, we have ac. Now this time it'll be minus mg, like so. Okay, and what I can do now is I get normal forces here, factor out the m, and I have centripetal acceleration minus g, like so. And I can go one step further here. Here's m. Now, centripetal acceleration, remember, is v squared over r minus g. Will get us how we can calculate the normal force, calculate speed, we have radius, we have acceleration due to gravity, and we have mass. Now, we want to look at the special case here. Okay? Remember, the normal force, this was providing the force here for it to go around in a maintained circular motion. Okay? So, the centripetal force is being supplied by the normal force to make sure it goes in circular motion. So what happens if the normal force is 0? The normal force is 0. Let's see what happens here. So this is 0 equals m. Here I have v squared over r minus g. Okay, so here the m can cancel out, And so what happens is that I have a G is equal to V squared over R, okay? Therefore, to solve for V here, V is going to equal the square root of G times R, okay? So this will be the minimum speed required for the cart to complete the loop. If it goes slower than this, therefore the normal force will be 0 and the marble or the cart will fall. So long as it maintains this speed or greater, it'll be able to go all the way around the loop here. Okay. Thank you. Okay, so now let's take a look at the cart or the marble when it's at the bottom region, when it's, let's say, down here. So it completed the loop, now it is at the most bottom region, and we will call this the bottom region here. And let's examine the normal force here. Okay. So what we can see here is that I have a normal force acting in this direction here. We have mg acting down this way, and the acceleration centripetal is acting toward the center. So wherever this is, you usually want to maybe call that positive. So we'll take going in this direction to be positive. Okay? So now when I do sum of the forces is equal to MAC, centripetal acceleration, the forces now is I have the normal force here minus mg is equal to MAC right here. So now the normal force will equal MAC, this will be positive mg, it's going to be plus mg. So the normal force is here, I can factor out m, and AC is V squared over R plus G, like so. So just like the tension problem, I can calculate the normal force here when it's at the bottom region. In fact, we'll call it B here for the normal force at the bottom. And notice now this is a positive G here, where it was at the top, it was a negative G. Okay, and from here we can calculate speed, mass, radius, G, and the normal force B. Okay, thank you very much.